So the goal of what I had you do here was to try to find a particular solution of this forced harmonic oscillator equation, forcing function 3 cosine of 4t. Because it's a cosine, an educated guess would involve a cosine, and yes, a sine, since the derivative of cosine is negative sine of 4t, with undetermined coefficients that would be the numbers in front of the cosine and sine, a and b here, are the amplitudes of the cosine and sine individually, but then you're going to add them up. It's a linear equation, so that when you add solutions, you get another solution. But we are after an entire sum here, specific values of a and b that give you one solution of this equation, called a particular solution. And do the same thing you always do. Take the derivative, take the second derivative, plug those things into the left-hand side of the differential equation. If it's going to work, what you want to do is you want to simplify it and set it equal to the right-hand side for all values of t. And ask, are there any choices for a and b that will make those things equal for all values of t? When you plug it in, you get this. Double check quick with me here. Y double prime, the cosine 4t term involves a negative 16a coefficient. 5 times the derivative, the cosine term involves 5 times 4b, which is 20b. Plus 6 times the function, the cosine term involves 6 times a. So that's where the 6a comes from. Do the same kind of thing with the sine terms. Simplify those coefficients. Negative 16a plus 6a is negative 10a. The 20b stays as is. Here, negative 16b plus 6b is negative 10b. The negative 20a stays as is. And again, you want this to equal the right-hand side of the differential equation, 3 cosine of 4t, no matter what t is. The only way that's going to happen is if this thing is 3 and if this thing is 0. So you get a system of linear equations. And we could certainly put it in a matrix and do row operations, but you don't need to if all you're after is an answer. What I did is I multiplied the first equation by negative 2 and added it to the second equation. Effectively, I was doing a row operation to get rid of the a terms. Negative 40b minus 10b is negative 50b. Negative 6 plus 0 is negative 6. B ends up being positive 3/25. And then if you solve for a using either one of these equations, a ends up being negative 3/50, giving you a final answer, yp to be negative 3/50 cos 4t plus 3/25 sine 4t. Okay. Now, having done all that, it's great, but it's not the main way that I want you to show your work for this kind of problem, actually. And if you watched the most recent lecture, you know that. Before I show you that other method, that is the main method I want you to use, I should mention something else. We are just finding one solution of this, not the general solution. This is not a general solution. We found A and B to make this a particular solution. To find the general solution, as usual with a forced equation, you have to consider the associated unforced equation or associated homogeneous equation. Y double prime plus 5y prime plus 6y equals 0. It's not the same differential equation. It is a new differential equation, but the solutions of this are related to the solutions of that. That's the whole point about the theory of linear operators. You guess with this kind of thing, e to the st, and you get the equation s squared plus 5s plus 6 equals 0, which can be factored as s plus 2 times s plus 3 equals 0. So s equals negative 2 and negative 3 are your eigenvalues, effectively. Your YH, general solution of the homogeneous equation, will be a linear combination of e to the negative 2t and e to the negative 3t. Add that to yp, and you have your general solution of the original forced equation. Notice this solution of the unforced equation, the homogeneous equation, is ultimately going to go to 0. It decays exponentially to 0. On the other hand, the yp does not decay exponentially to 0. So what happens to the long-term behavior of this mass on a spring that's following this model? In the long run, when t is large enough, no matter what your initial conditions are, the values of K1 and K2 don't matter. This term goes away. It is called transient because it goes away. It gets really, really small when T is really, really large. And in the long run, the sum YH plus YP approaches YP. This doesn't go away. It doesn't decay to zero. It reflects the long-term behavior of the oscillator. It's called the steady state. And this steady state is happening in spite of the fact that there's damping. The damping coefficient 5 is positive. That's what makes the transient go to zero. But because of the external forcing, ultimately, in the long run, the mass still oscillates back and forth and doesn't decay in amplitude. It's called the steady state. It's different than an equilibrium solution, right? Equilibrium solutions are constant. They could be constant functions that other solutions approach. In that sense, they could be steady states, but they are constant functions. This is not an equilibrium solution. It's not a constant function. It does oscillate, but it is the long-run behavior of this harmonic oscillator. So we still give it a special name. We call it the steady state. It's the long-run observed behavior of the oscillator. You should have, at some point in your past, maybe even in pre-calculus, thought about graphs of functions like this. It turns out they look like sine waves with a certain amplitude and a certain phase shift or phase angle, it's called. And for the rest of chapter 4, trying to understand that amplitude and the phase angle is a big part of what we do. And complex numbers are another big part of what we do. Here I'm now about to show you now the other way of solving for YP. That is the main way I want you to do it. Instead of considering the associated homogeneous equation, making this a zero, we consider what's called the associated complexified equation. Replace 3 cos 4t with a complex quantity whose real part is 3 cos 4t. Well, there's lots of complex quantities that would have 3 cos 4t as the real part. I could just make anything be the imaginary part. However, it turns out to be a good idea to make the right side be this, 3e to the I times, in parentheses, 4t power. That's called the associated complexified equation. Associated complexified equation. It is a new equation. It's not the same as the original equation. But when the original equation's forcing function on the right side is a cosine or a sine, when you complexify, you want to make it a complex exponential. And yeah, if you think about Euler's formula, this is the same as 3 cos 4t plus I times 3 sine 4t. The real part of this is the original right-hand side, 3 cos 4t. And we're going to use the nice properties that exponential functions have to help us solve this equation, and then use the solution of this equation to get back to this. You might wonder about what's the benefit of this. I'll talk about that benefit here in a few minutes. What do you guess? I could call it YP, but to distinguish it from the original YP, I'll call it YC. There's still an undetermined coefficient. Could call it capital A. Maybe to distinguish it, I'll call it little a. And since the right-hand side is an exponential, a complex exponential, a good guess is a constant times that complex exponential. And we got to solve for A like usual. But maybe A is a complex number. Yeah, that is what it will be. Take the derivative. Use the chain rule. You'll get an extra factor of 4i. right? And differentiating with respect to t. What gets multiplied by t up there? 4 times I. You need to have the 4t in parentheses. You don't have to, but I like doing it. For the second derivative, we get another factor of 4i from the chain rule. 4i times 4i is negative 16, right? Because I squared is negative 1. Plug those things into the left-hand side of the differential equation. Yc double prime plus 5yc prime plus 6yc. And what do we get? Negative 16a e to the I times 2t plus 5 times this one. We get a 20. There's our friend 20 from the previous page. Don't forget the I and the a and the e to the I 2t power. And then plus 6 times yc, 6a e to the I times 2t power. Simplify, you can, each term involves an e to the I 2t power. Did I make a mistake? That was a mistake on my part. Thank you. 4t. Those are all 4s. Pretend you never saw the 2s. Sorry. What's left after you factor out the a e to the I times 4t power? A negative 16 there, a 20i there, and a 6 there. Negative 16 plus 6 is negative 10. We've seen these numbers before. Plus 20i. We've seen the negative 10s and 20s before on the previous approach. I want to set this equal to the right-hand side here, 3 e to the I 4t power. Set this equal to 3 e to the I times 4t power. Solve for a. The only way these are going to be equal for all values of t is if those two things are equal. Therefore, a must be 3 divided by negative 10 plus 20i. We should simplify this. How? Trick, multiply by what's called the complex conjugate of the bottom. Multiplying the top and the bottom so we don't change the value of this number. Complex conjugate of negative 10 plus 20i is negative 10 minus 20i. You always take whatever sign, in this case a plus sign, is in front of the I term and make it a minus sign. If it had been a minus sign, I'd make it a plus sign. If I multiply it on the bottom, I also multiply it on the top to compensate. The nice thing that happens on the bottom is when you multiply a complex number times its complex conjugate, you get a real number. Negative 10 times negative 10 is positive 100. The outside and inside products from foiling cancel, right? Because outside times outside would be plus 200i. Inside times inside would be minus 200i. Last times last is minus 400i squared. I squared is negative 1. So the bottom becomes a real number. In fact, 500. On the top, multiply each term by 3, get negative 30 minus 60i divided by 500. That's the same as negative 90 over 500. Or no, excuse me, that was a mistake. Negative 3 over 50 minus 6 over 50i. Negative 3/50 minus 3/25 I. There's some familiar numbers as well. Negative 3/50 and, well, it's a negative 3/25 I. Whereas here we got a positive 3/25 I. What do we do with this? Plug it in back here and expand it with Euler's formula. and then take the real part. That's what we do with it. YP is going to be the real part of YC. RE stands for real part. We take the real part because the original non-homogeneous equation has a cosine on the right. If it had been a sine, we'd take the imaginary part. Because with Euler's formula, cosine is the real part, sine is the imaginary part. That's why. Real part of, go ahead and plug in the A that we just found. Then multiply by e to the I times 4t power. I've got to expand it though, I'm not done. Use Euler's identity. Now you actually don't have to multiply everything here. Because we're after the real part, we can use a shortcut. The real part of this product of two complex numbers is going to be first times first and last times last. Those are the two terms, the two products where the I is going to go away. First times first is negative 3/50 times cosine of 4t. Last times last, negative 3/25 sine 4t I squared. But I squared is -1, so the negative sign goes away. We get plus 3/25 sine 4t. And there we have it. That's the same YP as before. Like magic, right? Below your mind here. No, it's not magic. The textbook does go into the reasons why this works. Just feels like magic. What's the benefit? Seems like maybe more work. I mean, they were both kind of a lot of work, but maybe this is more work. What's the benefit? There are a few different benefits. One benefit of using the complexified equation is that if we had taken the imaginary part here instead of the real part, if we had done outside and inside products instead of first and last products, we get a particular solution of the exact same original equation, except with a sine there instead of a cosine, and we wouldn't have to redo work. That's one benefit. Another benefit of this approach is that this complex number here it's kind of like a secret decoder ring or something. It's got secret information about this trig function kind of hidden in it. What am I talking about? If you plot this complex number in the complex plane, I'll go ahead and do that. Negative 3/50 minus 3/25 I. This is called the complex plane here. We've had so many planes in this class, haven't we? We've had TY planes where we draw slope fields. We've had graphing the f of y versus y functions where we helped us make phase lines. We've had phase planes. We've had trace determinant planes, bifurcation planes, bifurcation diagrams. This is yet a new plane. The complex plane, it's called. That's called the real axis. This is called the imaginary axis. But you do see it. I did draw it there. It's there. Just labels. Don't get too philosophical on me here. How do you graph a complex number in the complex plane? You treat the real part as the first coordinate and the imaginary part as the second coordinate, negative 3/50 and negative 3/25. Negative 3/50, negative 3/25 a bit further away from 0. It's going to give you a complex number, say right about there. Let's pretend that number represents the real number, negative 3/50. And this number represents the complex number, the purely imaginary number, negative 3/25 times I. Then this number that has those two numbers without the I as coordinates would represent negative 3/50 minus 3/25 I. The secret information about this function that's sort of encoded by this complex number is found by figuring out its distance to the origin and also figuring out this angle. I meant this complex number here. A equals negative 3/50 minus 3/25 I. That complex number, what is its distance to the origin? It's denoted by the absolute value of A. It means distance to the origin. It's sometimes, instead of calling it an absolute value, people call it a modulus. Don't worry about that. It's just the distance to the origin. Just use the Pythagorean theorem. Square root of negative 3/50 squared plus negative 3/25 squared. No I in there because we're just thinking of these numbers, these real numbers, as being the coordinates of the point. Don't put any I there. That gives you square root of 9 over 2500 plus 9 over 625. Oh, a common denominator of 625 is going to make a 36 there, right? 36 plus 9 is 45 over 2500. That does reduce. 2500 divided by 45 is, okay, 55.55. They're both divisible by 5. I guess it's going to be square root of 9 over 500. Which does simplify. Square root of 9 is 3. You can rationalize the denominator and stuff, but I don't really care about doing that at the moment. Let's just approximate it. 9 over 500, 0.018. Take its square root, you get about 0.134. What I claim is this number, 0.134, is the approximate amplitude of this function. Say it again. This number, about 0.134, representing the distance from this point to the origin in the complex plane, represents the amplitude of this function. We'll see if it works in a second here. And this angle here, call it phi, but that's not the same as a flow or anything. It's just an angle label. Represents something called the phase angle of this sinusoidal function. And what does this angle equal? It's a little tricky because the point is in the third quadrant. You could use the inverse tangent function. The inverse tangent of essentially this number divided by this number. 3/25, negative 3/25 divided by negative 3/50 becomes, is 2, positive 2. However, I'm just using trigonometry there. Draw some triangles, you'll see it. However, that's not quite right. Because inverse tangent always gives you an output in the first or fourth quadrant. Our point is in the third quadrant of the plane. So to get to that angle, I need to subtract pi from this, 180 degrees. Let's approximate that. Inverse tangent of 2. Make sure you're in radian mode. Is about that, minus pi. This is approximately negative 2.034. Radians. If you want to convert that to degrees, just because you like degrees better, you can multiply it by 180 over pi. About negative 116 degrees, 0.6 degrees. Looks about right. What's the point? The point is this function is going to be approximately the same as 0.134 cosine of 4t plus phi, which means we need to do minus 2.034. Sorry, I'm out of room there. Why? I haven't said why. Let's just see if it seems right, though. Let's graph this function. This function here. Negative 3 over 50 is negative 0.06. Cosine of 4t. 3 over 25 is 0.12. Sine 4t. The period of this function is 2 pi divided by 4, which is pi over 2. So let's let x go from 0 to pi over 2. And we'll make the tick marks say pi over 8 apart. The amplitude is supposed to be about 0.134. So let me try negative 0.135 to positive 0.135. Pick something there. Let's see if it looks good or not. So this kind of cosine graph should fill up the screen here. It's a sinusoidal graph. It's not a pure cosine or a pure sine because it's not starting at the highest point or at 0. It's a cosine wave shifted to the right by a certain amount. There's a horizontal translation. Where does that maximum occur? Let's calculate it. Left bound, right bound. Yes. The maximum occurs pretty close to 0.51. Guess what? That's the same as 2.034 divided by 4. 0.5086. Remember that number, 0.5086. 2.034 divided by 4. Close. It's off slightly because of rounding. The horizontal shift of the cosine wave can be found or confirmed by factoring out 4 inside the cosine here, and in parentheses writing t minus 0.5086 or so. Sorry that I'm out of room here again. Remember in pre-calculus and in calculus 1, you learn about transforming cosine graphs, amplitudes and horizontal translations and stuff. That's what's going on here. That's the amplitude. T minus 0.5086 means that we take a cosine wave and shift it to the right by 4 up by that much, 0.5086. Maybe it seems like more trouble than it's worth. It's not more trouble than it's worth because you can do even more than what we're doing here. You guys are in electronics, right? You've dealt with this kind of thing in electronics too, right? What is it called? Impedance. You've dealt with this kind of thing in electronics. So it's a useful technique that is more useful than this even shows. The nice thing, again, that I'm showing here is that this complex number, the A, which is this, again, encodes the amplitude and the phase angle for YP, for the steady state solution. takes practice to get it, okay? Make sure you're practicing. You've got 15 minutes to do work today.